In this section, we're going to continue our conversation on Hamiltonian circuits. We're continuing the brute force method that we did in the last video, where we took the weight of each edge and added it up to try to get the lowest possible value. Maybe if our graph is a map, travel the fewest miles, or if it says it costs a certain amount of dollars to cross a certain edge, we want the lowest possible cost. In this case, when we did the brute force method, we kind of did it with smaller graphs where we only really had 6 or 8 circuits to worry about. There are times where we have millions upon millions of circuits to worry about. And so obviously we don't have time to do all of those. So we need a shortcut. This is called the nearest neighbor algorithm. And while it doesn't guarantee that we will get the lowest possible cost, it's saying close enough because we don't have time to do all of them. So step 1, choose a starting vertex. Step 2, go to the nearest neighbor. That means follow the edge with the lowest possible weight. Step 3, continue to the nearest neighbor unless it closes the circuit too early. So we're going to keep going along the lowest weight unless it's not possible because it messes up our Hamiltonian circuit. Sometimes that happens. We'll see an example of that in a minute. And then, of course, return to the starting vertex after visiting all the other vertices to finish off our circuit. So our first example here, it says, using the nearest neighbor algorithm, find an acceptable minimum cost Hamiltonian circuit starting from C. So we're going to start at C, and from C, we could either go to D, A, or B. Using the nearest neighbor algorithm, we're going to follow to D because that is the lowest weight possible. So C to D is 20. From D, I could either go to A or B. I am going to choose B because 40 is less than 70. We want the lowest possible value. And from B, really, it doesn't matter what the weight is. Our only possible stop is A. And then we finish off our circuit, going back to C, and that had a weight of 50. And so that all adds up to 120. So that's the weight of our nearest neighbor low-cost Hamiltonian circuit. Is 120 guaranteed to be the lowest possible circuit in our picture? Absolutely not. There might be lower ones, but we're not going to take the time to find every possible circuit. We are going to say this is close enough. In example 2 here, I know that's hard to read. If you have your notes with you, it might be good to follow along on that. So again, we're starting at C. What we should see is the lowest possible cost edge is over to D. And then the lowest possible cost edge from there is A. And from there, the lowest possible cost edge is B. And at this point, we should see a problem developing. From B, the only place I could go is E. And if I go to E, what's the issue with this? I can't complete my circuit. I can't get back home to C without retracing a vertex. And if I retrace a vertex, I've broken the rules of Hamiltonian circuits. So that means we need to go backwards a step or two. So I'll put the B back up there. And we can't keep going from there because we end up not being able to complete our circuit. So instead, let's back up to B. Let's try the second lowest Hamiltonian circuit, which takes me to D. Sorry, it takes me to C. My apologies. Third attempt, it takes me to E over here. Sorry, can't read it very easily. And then we go back up here. I'm sorry, folks. Let me try this again. Over here, we're at A. We're not at B. So we're at A, and we are forced to go down to B, because if we went to E, so sorry, folks. Again, I can't read the smartboard. I'm having to compare with my notes here. We go down to E. There it is. Because if we went over to B, we would be closing off our circuit too early, which is not allowed. So again, to recap, C to D to A, and then even though to B is the lowest cost, we have to go to E, otherwise we cannot finish our circuit. Then we could go to B, and then we could get back home to C. And so our weights there are 10 plus 12 plus 40 plus 30 plus 50, and it comes out to 142. Again, not guaranteed to be the best option, but it's definitely better than finding all the possible Hamiltonian circuits within this figure. This is a completed graph, I believe. Nope, sorry, not a completed graph. C is not connected to over there. So not a completed graph. So no easy way to calculate how many Hamiltonian circuits, but there's a lot of them. This next one, find the minimum cost starting in A. And what I should see is I have two options. I have two 7s. So which one do I go with? Really, it doesn't matter, whichever one you feel like. Let's say I chose C. From C, lowest cost would then be to H. From H, the lowest cost would be to G. From G, the lowest cost would be to F. From F, the lowest cost is to D. From D to E. And then even though it's not the lowest cost, it's the only way to get away from point E. We have to go to I, then B, then A. So that was A, C, H, G, F, D, E, I, B, A. And if we worked it all out, this comes out to a 103. That's a perfectly good answer. If you did that on a test, I would accept it. Let's see what would happen if we went the other 7. So A to D. Then we go to E because that's the lowest cost. Then to G because that's the lowest cost. F is the lowest cost. I'm kind of forcing my way over to H because it's the only place I could go. Then I could either go to C or I, but if I go to C, I'll put it in a different color just so we can see. If I go to C, then I'd go to B and I, and I'd be stuck. Don't want to get stuck, so instead we have to go to I, then B, then C, then A. That hit all the vertices. So that was and if we did that, that one actually came out to 83. So this is the better circuit to use. Although on a test or quiz, I would take both. Okay. Example 4, starting at point D, find the lowest cost. So from D, I should see that the lowest possible cost is this 28 over to C. From C, and by the way, when I see a number in the middle of the line, that means it's referring to that line. It's not referring to anything else. Like this could get confusing. Is the 41 talking about there, or there? It's talking about the middle of the whole thing. So that's what I'm looking at. So from C, 33 is a lot better than taking 51 or 44. From E, 46 is better than taking 48. From A, I pretty much have to go to B because if I went anywhere else, I would close the circuit too early. And from B, I have to go back to D because I've hit all my circuits. So that was D, C, E, A, B, and back to D. And if we added all of it up, it adds up to 185. Again, not guaranteed to be our minimum cost, but close enough because of time constraints. So that's it for nearest neighbor. We're going to learn another very similar method in the next video called sorted edges algorithm.